All right, continuing our discussion of derivatives, today we're going to look at one-sided derivatives. So if we take the limit as h approaches 0 from the right of our difference quotient, f of a plus h minus f of a over h, that's the right-hand derivative at a. And it may or may not exist. The same is true for the limit as h goes to 0 from the left of our difference quotient. That's the left-hand derivative at a. And again, that may or may not exist. Now, the only way that the derivative will exist if both the left and the right-hand limit exist and agree with one another. Okay? So that's what it says here. Just as with other limits, if the right-hand derivative at a is not equal to the left-hand derivative at a, then the limit as h goes to 0 of the difference quotient, f of a plus h minus f of a over h, does not exist, and f does not have a derivative at a. So let's take a look at a couple of examples. It's not going to be too terribly long today. So show that if f of x is equal to this piecewise function, x squared for x less than or equal to 0, and 3x for x greater than 0, that it has both left-hand and right-hand derivatives at x equals 0, but it has no derivative at that point. Okay, so the first thing I'm always going to do on this is find what is f at 0, because it's asking me to find the derivative at x equals 0. Well, that's going to be 0 squared, because when we're equal to 0, the branch defined by x squared tells me what happens there. So that's 0. So when I do a left-hand derivative, I'm going to do the limit as h approaches 0 from the left of f of 0 plus h minus f of 0 all over h. Part of the reason I'm taking the time to write that, you don't have to necessarily write this, but I want to do it because sometimes there's so many zeros involved, like on this one, because we're doing it at 0 and there are lots of things that are 0, it's easy to get lost. So kind of start with the basics, fill in the a, and then start thinking about the limit. So that's going to be the limit as h goes to 0 from the left of, so if we're looking at h going to 0 from the left, well, that means that we're going to be using x squared, right? So this is going to be 0 plus h quantity squared minus f at 0, which we already know is 0, all over h. So that'll be the limit as h goes to 0 from the left of, when I expand this, that'll be 0 plus 0h plus h squared minus 0 all over h. So that's the limit as h goes to 0 of h squared over h. We can simply do the division there, because we're not dividing by 0, because it says h goes to 0, not as h is equal to 0. So this will be the limit as h approaches 0 of h, which is 0. So the left-hand derivative is 0. So now let's find the right-hand derivative. The problem has already told me that this limit is going to exist, but that it's not going to be the same as the other one. So start off the same way. The limit as h goes to 0 from the right of f of 0 plus h minus f at 0 all over h. So it's the limit as h goes to 0 from the right. And if we're coming from the right of 0, we're using 3x. So that'll be 3 times 0 plus h minus f of 0, which is 0, all over h. So this would be the limit as h goes to 0 from the right of 3h over h, which would be, again, dividing the limit as h goes to 0 of 3. There's no more h, so that's just equal to 3. So the question is, well, what the heck is going on here? Well, we'll talk more about something called differentiability, I think tomorrow. But what's happening is this. On the left side, you've got the curve y equals x squared, which is a nice little parabola, and it looks something like that. And it goes through 0, 0. On the right side, it doesn't include 0, 0, but that's kind of where it starts. You know, put that in quotes. It's a line with a slope of 3 and a y-intercept of 0, except it doesn't actually have that intercept. So you've got this line going off here like this. And again, we'll talk more about this tomorrow, but this is part of leading into tomorrow's lesson. We notice that as we move towards 0, 0 from the right, the curve has a nice slope. Everything's great. It looks like it's going to be 0 at 0. But then we look at the other side and we're like, oh gosh, over there the slopes are all 3, right? So since the slopes are all 3, we have this incongruity. One side says it ought to be 0. The other side says it ought to be 3. And they don't agree. And anytime the left and the right don't agree, well, that's bad. And you can take that any way you like. All right? So, yeah.
Oh, I was just going to ask, if we see this problem on a test, could we just say, like, 3x, the derivative is just got to be 3 because it says that it has a slope of 3?
Yes, you could. I would accept that. Because as we move towards, now you have to be careful, and I'll show you something that it looks like it ought to on the next one, but it doesn't work. Okay? I have one actually cooked up specifically for that question. Every now and then I think ahead. It's like I've done this before. Yeah. I think it's my second favorite phrase to say that this is not my first rodeo.
What's your first favorite?
Hold my beer. Which is funny on multiple levels, mostly because I don't drink beer, but the idea of, you know, someone says you can't do that, and I'm like, yeah, hold my beer. So anyway, I just always have found that to be really funny. All right, so let's take a look at this. And I realized when I was reading this morning that I had worded it. It was clunkily written. It was, anyway, so it reads better if you change this, it was caused to causes, and change, I don't remember what this was, is change it to 2. It reads much more smoothly if you'll change that on yours. So again, we have a piecewise defined function, and they want us to show that where the two branches come together, that f doesn't have a derivative at x equals 3. And the question is, what about the graph of f at x equals 3 causes f to not be differentiable at x equals 3? Yes?
The signs are both the same on the x is less than 3, because one is less than.
Oh, I apologize. So many mistakes. Let's change that. Thank you. Now, this is one where if you just casually looked at it, you would go, oh, the left-hand branch and the right-hand branch both have a slope of 2. That should be fine. It's unfortunately not, for a different reason. So let's take a look. First of all, like we did on the last one, I'm going to figure out, well, what is f at 3? F at 3 is going to be 2 times 3 plus 1, which is 7. So I'll start with my left-hand derivative. And you might guess that it's 2, but it's not. Let's show why. We're going to take the limit as h goes to 0 from the left. So as h goes to 0 from the left at 3, I'm going to be looking at the 2x minus 1, right? As we're coming from the left. So that's going to be f of, I'll go ahead and do like I did on the last one, 3 plus h minus f at 3 all over h. It's really over 3 plus h minus 3, but the 3's always drop off. That's why we just write the h. So this will be the limit as h goes to 0 from the left of 2 times 2 times 3 plus h minus f of 3, which is 7, all over h. So that's going to be the limit as h goes to 0 from the left of 6 plus 2h minus 7 over h. Well, let's see. That's going to be the limit as h goes to 0 from the left.
What about the minus 1?
The minus 1.
2x minus 1? It's 2x minus 1?
Oh, thank you.
I also think that would make it
Yeah.
not 7.
So that's going to make it
5.
6 minus 1 is 5, minus 7 is negative 2. Now, with that one, I'll have the limit as h goes to 0 from the left of negative 2 over h plus 2. as h gets close to 0, what happens to this fraction? It's undefined because it gets really big, right? Now, let's think about the sign of it. I'm using negative numbers near 0, and I'm dividing that into a -2, so that's going to be infinitely large. Plus 2, and they're like, okay, fine. Add 2 more to something really enormously big. This is infinite. The left-hand derivative does not exist. And I'll show you why in just a second. But let's go ahead and do the right-hand derivative, because we might have done that one first. The right-hand derivative will be the limit as h goes to 0 from the right of f of 3 plus h minus f at 3 all over h. So that's going to be the limit as h goes to 0 from the right of, what was it? It was 2x plus 1. So that'll be 2 times 3 plus h plus 1 minus 7 all over h. So that's the limit as h goes to 0 from the right of 6 plus 2h plus 1 minus 7 all over h. And this one does kind of what we're more used to, right? All the constants in the numerator drop out. We've got the limit as h goes to 0 from the right of 2h over h, which is our expected 2. And you're like, okay. So I could have stopped after finding that the left-hand derivative doesn't exist, right? Doesn't exist can't be equal to something else. But why is this happening this way? It feels like both of these ought to have a slope of 2. But here's the deal. So if I'm sketching a graph of this, I really didn't need that to be anywhere near that high. So I know that this goes through the point 3, 7. And then to the right of that, it follows the graph 2x plus 1. So that's going to start at the point 3, 7 and go up with a slope of 2. And I've drawn mine so close to here that it's going to have a little break there, which is what we found. For the other one, it's supposed to follow the graph of 2x minus 1, which, if we get close to 3, gets close to 5. So parallel to the other one, but there's this jump discontinuity here. And when we were finding the slope of the derivative, what we were doing is we're connecting points over here to this point. And you can see how those get closer and closer to positive infinity the closer I move this point to this hole. Okay, so what about the graph of f causes this to not be differentiable at x equals 3? A jump discontinuity. That jump discontinuity causes problems for us. It turns out that if a function has any discontinuity at a point, then it will not be differentiable at a point or at that point. And if you think about it for a little bit, that kind of makes sense. How can you have a tangent line to the graph of something at a point if that point doesn't exist? It doesn't really make any sense. All right, questions? Okie dokie. Like I said, most of this is leading into